Hello, data structure students. I hope you're all doing well, staying happy, healthy, and safe. And today we're doing a special video talking about some code that you might not have seen before. Because after all, you are very early in your careers as computer scientist. And for your next assignment, we're going to be doing some really special stuff. We're going to be looking at empirically comparing the runtime of search operations on different data structures. Comparing specifically the performance of searching for an arbitrary value in a linked list versus searching for an arbitrary value in a binary search tree under different conditions too. But there's some things that you might need to know for this that you may not have already seen in your other classes. So we're going to give you some copy and paste code today that you can utilize in your assignment as a tool. Use it as a hammer to get something done. And like I said, this is code that you're free to copy and paste into your next assignment in order to do the timing and randomization stuff that we're going to talk about. So the first thing I want to talk to you about is generating random numbers, because an important part of your next assignment is generating a random set of numbers that you're going to propagate. You're going to fill your linked list and your binary search tree with. And you might have seen this already, you might not, but I'm going to show you some quick and simple ways to get a series of random numbers. So let's go ahead and get started. We're going to work this out in a file. We'll call it rando.cpp. And first things first, I'm going to set up the basic vanilla framework for a small C++ program, things that you've seen. So we're going to want to output some things. Let's go ahead and get our IO stream in there. We're going to set up standard namespace. Going to make a main function. Looking great. And for our purposes, we're always going to return 0. Okay, so we got the skeleton of the most simplistic C++ function in the world. Now, to generate a random number, you're going to need to, find some randomness. The problem is that your computer is deterministic. And we need to find a way to generate a random number deterministically. And this is where pseudo-random number generation comes in. Pretty much all of the random numbers that you've worked with in your code or in other programs that you've utilized have been pseudo-random numbers. They're not really random, but they're random enough. And I'm going to show you how to generate some simple pseudo-random numbers today. And here's how easy it is, sort of. Rand is a random number generation function. Let me show you what it does. Let's output the value returned by rand. Okay. So let's save this, we'll go over here, and we'll start to compile it. Okay, so compiled our code, and now let's run it. Okay, so pick a number, any number, just guess a number, right? Got a number in your head? Good, let's run our code. It wasn't that number, probably. So, yay, we have a random number. Let's make more random numbers. We'll go over here and we'll copy and paste rand over and over again and save it. Now we'll compile it. We'll run it again. Whoa, those numbers are different from each other. But wait, oh my goodness, I see a problem. The first number is the same. This could be a coincidence. That's how randomness works. Sometimes you'll randomly get identical numbers back to back. But is that what's happening here? You can tell by the tone of my voice it's not. But let's pretend it is and go on. Okay, it might be randomness. Let's run our code again and see what happens. Oh no! We got exactly the same set of numbers. Now, each one of these numbers is different than the previous number in that run of the program. But between runs of the program, we get the same list of random numbers over and over again. And that's not very random. So what I'm not going to go into the specifics of like how pseudo random number generation works, but an important part of that is seeding your random number generator with a starting value. And so to do that, there is a special function called srand. Srand takes an integer value as input. It can be anything. Takes an integer value as input and uses that as a starting seed for your pseudo random number generator. So it uses that as input, like, okay, I don't know what this number is. User gave it to me. I'm going to plug that into my pseudo random number generator and use that to generate better random numbers. So let's save our code. Let's compile it and see what happens. Okay, that's a different number. Oh my goodness. I like this already. That is a different number here than this. Perfect. And it's also not one of the numbers in this list either. Looks like we're getting more random, right? Okay. Let's do this a couple more times. Let's recompile our code, run it, and oh wow, look. This number is different than that number, it's different than that number, it's different from that number, it's different from that number. But oh my goodness, look at this one. It's the same number from the last run. Again, randomness is funny. Could be a coincidence. We're scientists here. We got to check this out. So an easy way to check it out is to run your code again. See what you get. Oh no! We get the same list of numbers again. Now, this list of numbers is different than the one that we had before when we weren't using srand. But it's still the same set of numbers over and over and over for that random seed. So it's not sufficient for your seed to be arbitrary. It's not even sufficient for it to be random. It's got to be unique. So you have to put a unique number in your seed function every time you run your program, a number that it hasn't seen before, if you want a unique set of random numbers each time. So how do we do that? That's hard. Like, are we going to have the user type in a random number to seed it every time? No, you're not going to do that. Have you ever had to type in a random number? I mean, maybe like when you're like setting up like SSH keys or something. If you don't know what I'm talking about, ignore it. But usually you don't have to randomly seed, your functions for your programs. It figures out a way to do it on its own. And the key is in something that I said. The seed doesn't have to be random, but it must be unique. Well, there's one thing inside of your computer that will never repeat, and that is the timestamp. Time only marches forward. So if you use your timestamp, like the current date and time on your computer, as your random seed, it's going to give you a different set of numbers every time you execute it. Now, how do we do that? How do we get the timestamp out? Well, guess what? There's a function for that too. And you might be surprised to learn that that function is called time. Now, if you want to look up the nuances of the time function, you can look at its man page. But in a nutshell, it gives you timestamps. Now, you can pass parameters into this thing to get timestamps from different points in time. But usually, and especially for our purposes, we don't care about the past or the future. We care about now. What is the timestamp right now? And so if we want the timestamp right now, we pass a null pointer as the input parameter to our time function. And it's going to return the current time in seconds. Remember that I said that. It's going to return the current time in seconds. So let's save our code. Let's go back over here and recompile it. And let's run it. Okay, those numbers look kind of random. I like them. Let's run it again. Oh my goodness. That is a different set of 5 numbers. They're not the same. This is nice. I like it. Okay, a different set, a different set, a different set. My goodness. This seems to be the perfect solution for generating random numbers. Let's just keep generating some more. Ooh, random number, random number, random number, random number, random number, random number, random number. Oh, wait. They're so random. This is so cool. Let's keep going. Oops, I did not mean to clear the screen. Oh no! What? Look at this. We got the same set of random numbers. Dr. Jones, you told us that that wouldn't happen if we used the current time. But I told you to remember something too. The thing that I told you to remember is that time returns the timestamp in seconds. So if you run your code really, really, really fast, and you happen to run it twice within 1 second, the timestamp is going to be the same, and you're going to get the same set of random numbers. That's something to keep in mind, not so much for this assignment, but for things that you do in the future and perhaps things that you do in the wild when you're coding for a job. To reduce the likelihood of this happening, you want to seed it with a timestamp that is at a higher resolution than seconds. And we're going to look at a way to get timestamps in higher resolution than seconds in our next code example. But before we move on to that, I want to talk a little bit more about rand. So one of the things that at some point in your career, and by at some point in your career, I mean like for the next programming assignment, you're going to want to get numbers that are on a specific range. So if we run our code as we've got it right now, we get really big numbers, like on the range of from 0 to blah, 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 big, really, really big numbers. If you want to know the actual upper limit, read the man page for the random function. But it's a really, really big number. We don't always want really, really big numbers. We might want a number to only be in the range of from like 0 to 99. In that case, we need to find a way to take an arbitrarily big number we don't know how big it is, and be like, let's math it and get it on a range of 0 to 99 or 1,000 or whatever. So we can exploit a mathematical function that gives us the remainder of division. And this is called modulus, or we usually say just mod for short. And that operation is represented with the percent sign. So we can generalize this as saying if we take a number and we mod it by another number, the result is always going to be on the range from 0 to 1, or the modulus number minus 1. So for instance, if we wanted values on the range from 0 to 5, we would mod it by 6, one greater than that. So we'd have 0, 1, 2, 3, 4, 5, 6, or 0, 1, 2, 3, 4, 5. So let's save our code. Let's compile it, and let's run it. And look at that. I'm executing it far too fast. Look at that. All the values are on the range from 0 to 5. Beautiful, gorgeous, 0 through 5. Now, for your upcoming assignment, you're going to have to normalize your random numbers to be random, but within a certain range, like from 0 to 1,000 or something like that. Okay, and so for that, you would, change the number that you're modding the output from your random function by. Now, sometimes, not necessarily for this assignment, but sometimes you're going to want to have numbers that be like a range from like negative something to positive something. You can math that out too. So let's say we wanted values positive 50 to negative 50, negative 50 to positive 50. Now remember, if we do mod by 100, that's going to give us values from 0 to 99. And if we subtract 50 from that, that's going to move it down 0 down to negative 50, and our upper bound to 49. But if we want negative 50 to positive 50, we'll need to do this by 101 and then subtract 50. So let's recompile our code, clear our screen, and execute it. And you see we've got numbers. Now we've got negative numbers coming out. Lots of negative numbers. That's how randomness works. There's some positive numbers. Excellent. Okay, so using this code, you can copy and paste this into your next assignment and use that to generate the random numbers for your data structure. The next thing we're going to be doing, though, is arguably even cooler. And that is timing the execution of code. So another really important part of not just being a programmer, being a computer scientist is thinking like a scientist. You want to evaluate, your expectations about the code that you're using or whatever procedure you're messing around with. And so for your upcoming assignment, you're sort of going to be engaging those processes. You're going to be timing how long it takes to execute a search with a linked list versus with a binary search tree for different kinds of input data. And to do that, you're going to have to get really, really high resolution measurements of how long that code takes to execute. And that can be challenging. And it's unlikely that prior to this class you've seen this. So what I'm going to do is today I'm going to give you a copy and paste tool, a hammer for you to use in your code to do these measurements of code execution. So we're going to start off by getting our usual stuff that you'll see in your generic C++ program. Okay. You're going to need one more thing. You're going to need to include the chronometer library. So include chrono. Okay. And by the way, for this code and the code that we just went over, don't worry about copying it from this video. I'm going to have slides on the website adjacent to your class lecture slides that has this code in it, so you can look at it and reference it directly. It'll be better formatted. It'll have comments in it. It'll be a lot better than the examples that we're working through today. But I want to do some examples live to kind of show you how this thing works. Okay. So if we're going to time how long a piece of code executes, let's pretend that you've got code here. We'll just say your code in this little comment block and let that be where your code's going to go. If we want to figure out how long it takes, we're going to have to record the time before your code executes and then the time immediately after your code executes. And we can use the chrono library to get a super high resolution timestamp before and after you execute your code. And that's going to look something like this. So we're going to set our start time equal to chrono, high resolution, clock, and we want to get the current timestamp. So we'll say now. Okay, cool. Now we'll use this same code to get our end time. Okay, and for those of you watching at home, you just heard the most horrendous sneeze in the world coming from the other side of the room. Sorry. I'm joking. I'm recording this from the lab. There's people here. They've got jobs. They do stuff. And sometimes people who do stuff sneeze. And that is okay. But you'll notice there's something that I left out of this example. I've made a variable, hypothetically, start time and end time, but I didn't give it a data type. Well, here's where some more of that voodoo magic comes in. You don't always want to use the trick that I'm about to show you. But for things like this, where the return type is complicated, we'll say, there's actually a special thing you can do. And you've probably been taught that C++ doesn't do this thing. You can actually assign it as an auto data type, meaning it's going to say, okay, I'm making a variable. I don't know what data type it is. Let me look at what's being assigned to it. Okay, that's the data type. We're going to use that. And that's what auto does. Usually when you ask people if C++ does automatic data typing, they'll say no. It is actually a feature. It's just not one that you should always use. For things like this, where the return type of this timer function is a little bit complicated, it's okay to use things like auto. And if you don't get it, that's okay. Like I said, use this code as a tool. It's a hammer for you to do a specific part of your next assignment. Okay, cool. So now we need to calculate how long it took. So a duration. And duration is going to be equal to your end time minus your start time. Okay, cool. That makes total sense. However, there is a small problem. We need the time in something that makes sense to humans. Turns out chronometer, your chrono library, is going to effectively be measuring your time in CPU ticks. How many sequential operation times, like little segments of like, I'm going to do this operation, execute. And that's dependent on the speed of your processor. Well, if I'm running it on my laptop, I'm going to get a different set of CPU ticks than if I'm running it on my desktop at home. Now, those are really, really high resolution measurements, but we need them in something that's going to be consistent from platform to platform, that's going to also be human readable. For this example, we're going to be using microseconds, a teeny, teeny, tiny duration. And to do that, we're going to do chrono duration cast and set its templated type to chrono microseconds. Awesome. Okay. And just like with the others, we can auto data type this one. Okay. Cool. Now, effectively, what it's going to do, this is not 100% accurate, but it's a good conceptualization, is it's going to make a list of timestamps, all at microsecond intervals. But to get the real duration, we don't want to know, like, okay, this timestamp was here, this timestamp was here, this timestamp was here. Since they're all separated by 1 microsecond, we can just count how many entries there are in that data structure, and that tells us how many microseconds elapsed over the period from our end time to our start time. And so we're going to store that in something that makes a lot more sense, a long integer type. And so we're going to get our value in microseconds, and we're going to get that by doing duration dot count. Okay. Now let's output that information. Okay, time taken by code segment. And let's put it on a new line. We'll tab it over so it's nice and easy to read. And output microseconds. Let's give it a unit. All right. Okay. So I have just freestyled this whole set of code, and now we're going to compile it. There's probably going to be typos. If we're really lucky, there won't be, but there's probably going to be some typos. So you're going to get to see me debug some stuff. Yay, right? A nice authentic representation of how coding works. Okay, so let's compile it, and it compiled the first time. That's rare. Okay, cool. But remember, just because the code compiled doesn't mean it's correct. It just means that it's not broken, like broken down on the side of the road broken. We still might be slipping gears, but we can at least move. So let's execute our code and see what we get. Time taken by code segment 0 microseconds. Well, that doesn't make a lot of sense, does it? Well, what was our code that we put over here? There is no code. It's just a comment that says put your code here. So let's let's do some experimentation. We got a framework now that'll let us time how long a piece of code takes to execute. So let's put some stuff in there, huh? Okay. So another thing I love about tools like this is that it lets you not take for granted things that you're told in class. For instance, whether you're ECE or CPE or CSE or SC or CISO or whatever major you are that's usually taking this class or not usually taking this class, chances are at some point in your educational career prior to now, a professor has said divisions are more complicated operations on your CPU than additions, or it takes longer to do floating point arithmetic versus integer arithmetic. And you were like, okay, that's good for me. And then you moved on with life. You memorized it, you probably wrote it on a test, and you went on. But here's the thing. That's not how science works. In science, we have to test things. And so let's see if those claims are actually true. Let's see if, say, addition operations are faster than division operations. So let's make a float value here. We'll just call it num. We'll set it equal to, I don't know, something arbitrary like 12,345. And down here, let's do a bunch of, say, divisions on it. Okay, so let's say we're going to do 100,000 divisions of this. So we're just going to take num and we're going to divide it by 100,000 times. Let's see how long that takes. Let's save our code. Let's compile our code. And let's execute it. Okay, that's a pretty long time. 713 microseconds. Okay. Let's see what happens if we change one thing. Instead of doing divisions, let's change this from a divide to an add. So look at a floating point addition instead of a division. Now let's compile our code. And we'll execute our code. And look at that. It took about half as long. It was twice as fast. Doing addition versus division. And you get told that in class, but you never actually get to see it usually. Well, using a method like this hammer that I've now given you, you can go and empirically look at this stuff. If you're interested in how long a segment of your code is taking, and if I do it this way versus this way, how much faster is it going to be, you now have the tool to go and do that. So it's really cool, and that's what you're going to be doing for your next assignment. You're going to be taking a linked list and a binary search tree and filling them with the same set of values, and then performing a search on both of them and timing how long that search takes. And we've told you in class that if you're searching a linked list, on average, you're going to have this runtime. If you're searching a binary search tree and it's well balanced, you'll have this runtime if you've got on average. And if you got a binary search tree and it's poorly balanced, your runtime is going to be more like this. Well, now you don't get to take our word for it. You get to see it in practice. And that's the whole point of the next assignment. So all the code that I'm giving you here is on Canvas. You can copy and paste it, put it into your assignment. The one on Canvas is going to be better formatted, have better comments. So, you don't have to worry about tippy-tapping all the code that's on the video right now, because you can go onto Canvas and just get it. If you've got questions about this stuff or you're having trouble getting it to execute, get in touch with myself, get in touch with the TAs, get in touch with SI, get in touch with somebody. Talk to your classmates. There's a lot of opportunity to from people who are going through the same problems that you're going through. So talk to the people, talk to the TAs, talk to me. If there's anything we can do to help, we want to help you out. But you got to ask. All right. So with that said, I hope you're all doing well, and see you in cyberspace and/or class.